verification of Thevenin's theorem and as well as Norton's theorem. Thevenin's theorem and Norton's theorem. First of all, I am taking one simple circuit here, Thevenin's theorem, to verify the Thevenin's theorem. This is the load. This is the load we are taking here, and the value of load is 200 ohms. 200 ohms, and the supply is given as 220 volts DC supply, and the same value I am taking 150, 100 and 120 ohms resistor. So here the Thevenin's theorem statement is nothing but in a linear bilateral network consisting of number of voltage source and resistance can be expressed with a single voltage source in series with a resistor. Resistor is nothing but its internal resistor. So this can be written as like this. So this entire circuit can be represented with single voltage source and in series with the resistor. So this is R Thevenins and this is Thevenins voltage, and across this the load is connected. Across this load is connected. So here our intention is to find out this Thevenins voltage and as well as Thevenins resistor, so that we can calculate the load current which is flowing through this load 200 ohms. So this IL can be written as V Thevenins divided by R Thevenins plus this RL. RL is nothing but load resistor. So for that, first of all, what we have to do means we have to remove this load resistor. Then for that we have to calculate the V Thevenins and as well as R Thevenins. So if I remove this load, then the circuit will become now like this. So open end terminals, terminal A and B will be open like this. Now for this case we have to calculate the Thevenins voltage. The voltage across the open end terminals is called your Thevenins voltage. So this is the value 220, 150, 100 and 120. So here the Thevenins voltage is nothing but where we are opening the load, across that points only the voltage appears. That voltage is called Thevenins voltage. So as it is a open end wire, so here the voltage which is appearing here, this is called your Thevenins voltage. This is our Thevenins voltage. So for this Thevenins voltage is nothing but this circuit is now opened. So here it is forming a simple closed path. So if I know this current flowing through this path, then I can calculate the voltage across this resistor. So here the current can be calculated as 220 divided by this resistor 150 plus 100 ohms. So this can be 0.88 amperes. Then voltage across 100 ohms can be written as 0.88 into 100 volts. 100 ohms is nothing but our Thevenins voltage VTH, which is equal to 88 volts. This is our Thevenins voltage. And if I want to calculate R Thevenins, so for this we need to redraw the circuit again by replacing the sources with their internal resistances. That means voltage source can be short circuited and current source can be open circuited. So here in the circuit we are having voltage source, so I have shorted this one and the values are 150, 100 and this is 120. So I need to see from this end to calculate the R Thevenins. So therefore if I calculate from if I see from this end, we need to calculate from the other end. That means 150 and 100 ohms are in parallel and the resultant is in series with the 120 ohms. So therefore my R Thevenins can be written as 150 into 100, both are in parallel and the resultant is in series with the 120 ohms resistor. So here if I compute this one, my R Thevenins will become now 180 ohms. So this is the 60 ohms and this is 120 ohms, is nothing but 180 ohms. So I calculated V Thevenins and as well as I Thevenins, 180 ohms. So here this V Thevenins is 88 volts and R Thevenin is 180 ohms. Then I can calculate the load current IL is equal to V Thevenins, this formula. I am using this formula. V Thevenins is nothing but 88 divided by 180 plus load resistance is 200 ohms. So this can be my load current 231 amperes. So here this is the Thevenin's theorem, and in the Norton's theorem calculation of RTH is same. So in the Norton's theorem calculation of RTH is same. So there we'll calculate the RTH value as 180 ohms. And here we need to calculate the Norton's current from the same circuit. We'll see now. So this is the Norton's theorem verification, and we have calculated the Thevenin's resistance RTH, which is nothing but 180 ohms, which is same in case of Norton's resistance and Norton's theorem also, RN. So RTH is nothing but our Norton's resistance, no need to calculate again. So here this is the given circuit. So this can be represented with a single current source in series with the in parallel with the internal resistance or Norton's resistance, and this is my Norton's current source and this is my Norton's resistor, and the load is connected in parallel with this. The load is connected in parallel with the source. So here this is my representation of the Norton's theorem. So here in this case we need to calculate I Norton's and as well as R Norton's. R Norton's is very much similar to Thevenin's resistance RTH. So calculation of Rn is over. Now I need to calculate the Norton's current, which is nothing but in the Thevenin's theorem we have opened the circuit and we have calculated the open voltage, the open circuit voltage across these load terminals A and B. But in case of Norton's theorem, we need to short the circuit. Then we have to calculate the current flowing through this short circuit branch. So that is my Norton's current. So here if I want to calculate the Norton's current, so I can apply KCL here. You can apply KCL at this node. You can calculate the Norton's current. Or we are having another method that you can calculate the equivalent resistance value, then calculate the total current. Then by using the current division principle, we can calculate the total current, this Norton's current. So by using two methods we can do. So here I am going for the second method. So first of all I am calculating the R equivalent value. That means these 100 ohms and 120 ohms are in parallel. 100 into 120 divided by 100 plus 120, and this entire equivalent value is in series with this 150 ohms. So here this will be 204.54 ohms. So now I wanted to calculate the total current flowing through the circuit, which can be written as 220 divided by 204.54. So this is 1.07 amperes. So this is the total current flowing through this circuit, 1.07 amperes. Now I wanted to calculate this Norton's current. So therefore I have to use current division principle. Then I Norton's can be written as this total current 1.07 into parallel branch resistance 100 divided by 100 plus 120, which is nothing but 0.488 amperes. So this is my Norton's current. IN is equal to 0.488 amperes, and Norton's resistance is 180 ohms. Now I have to calculate this load current value. So I know IN and I know RN. So current division principle again. So IL is nothing but I Norton's 0.488 into parallel resistance RN 180 divided by 180 plus load resistance 200. So this will be 0.232 amperes. So for the same circuit, I got the load current in Thevenins theorem as 0.231, and in the Norton's theorem I got the load current as 0.232. So in both cases the value of load current is same. And another thing here, in the Thevenins theorem I have taken the circuit like this, and in the Norton's theorem I have taken the circuit like this. So this means it is simple source transformation technique, VTH, RTH, I Nortons and RN. So here across this we are connecting the load. So if you are using both the theorems, you need to get the same value. So source transformation technique, here we can apply source transformation technique directly. So it's a simple source transformation technique. So while converting voltage source into current source, we are using the Ohm's law principle. IN is equal to VTH by RTH. And the value of RTH will be same when you are connecting, when you are converting it as a current source. So is it correct or not? Let us see from this. So we know the VTH value. VTH value is 88 volts and RTH is 180 ohms. So this is nothing but 0.489 amperes. So we have calculated the Norton's current as 0.4889 amperes. So both are same. So we can directly calculate from the source transformation technique also. Open the MATLAB account, and there we are having Simulink option. After pressing on Simulink option, a new window will be opened, and there we need to select a blank model. So to make the circuit active, I have selected power give component. So it will make the entire circuit in active position, and the DC voltage source as a power supply, and I'm considering the series RLC branch component. So from that I'm considering only resistor. So change the parameter into a resistor value, and I'm giving the value of resistor as 150 ohms as we have taken in the theoretical part. To change the resistor value as 100 ohms. Another series branch resistor value is 120 ohms, and this is my load resistance 200 ohms. So connections are made as per the circuit diagram, which we have discussed in the theoretical part, and the DC supply is given as 220 volts. Now to measure Thevenins voltage, we need a voltage measurement component. So that block I have considered here, and also to know the value, we are having a display component here. So both are connected across 100 ohm resistor, because as we are opening the load resistance, the Thevenins voltage will be the voltage across the 100 ohms resistor only. So for that reason, I am opening the terminals A and B such that the load resistance will be removed from the circuit and the Thevenins voltage will be calculated across 100 ohms resistor. Run the simulation for 0.6 seconds. Then note down the reading of Thevenins voltage and compare with the theoretical value. To calculate the load current, take a current measurement block and connect in series with 200 ohms. Then run the simulation. Now we are able to calculate the load current